Today we're going to start talking about RC circuit. This is an RC circuit. This is a resistor connected to a capacitor, and there is an indicator, something that to measure what's going to happen to the charge on the capacitor with time. So what I'm going to do is I'm going to connect a battery, and I will charge that battery, that capacitor. I will charge the capacitor, and I would like you guys to look carefully on what happens to the lamp, to the light bulb. It's going to happen all the action is going to happen in a very short period of time, but I want you to look at what's going to happen. Well, it lets, then I disconnected it, look at it. What happens? Fades away, and the capacitor is discharging, then it takes time to discharge, then it goes to zero. So if I do it again one more time, it takes time to build the charge. Oops, sorry. It takes time to build the charge. Then when I disconnect it, it takes time to discharge the capacitor. What we are interested in today is to find at any time t, what will be the charge on that capacitor when we charge it or when we discharge it. At any time, we need an equation to describe that can describe to us the charge on that capacitor as a function of time t. That's what we need to do. And with that circuit, we call it an RC circuit. This is the circuit that you see on the board now. This is the RC circuit. This is the summary. This slide summarize all what we're going to study today. R for resistor. R for resistor. Okay. R is for resistor. C is for capacitor. So now I'm in this configuration here. I'm charging the capacitor, and I need to describe what will be the charge on the capacitor as a function of time t. Here, if we switch the switch, Rami, if we switch the switch from A to B, that means that we're disconnecting the battery. The battery is not going to be in the circuit anymore, and now we are discharging the capacitor. And in those two circuits, I need to draw this curve. I need to prove those two equations that describe to us the charge as a function of time t, the charge at any time t, and we need to prove those. So I'm going to start this by telling you a little bit about.
Doctor?
Yes.
That's all right.
Sure.
Maybe a second. For example, one of the lessons, key bulb, for example, in the circuit.
Yeah.
When we're charging the capacitor, bulb.
Yeah, we put the bulb here just to indicate how much current is in the circuit, and that bulb we choose it in such a way that it has very small resistance compared to that resistance.
Okay, it will light when it's charging and it will light bulb when it's charging.
Yes. You weren't here, right? You came late. You missed the best part in the lecture. So again, I'm going to charge it. Okay, and I will discharge it. Takes time to dissipate the charge away from the capacitor. The charge gets dissipated in the resistor, and it fades away. The light, that means that actually the charge is dissipating away, and it takes time.
The time it takes to fade away depends on the time we charge the capacitor.
Oh, well, we'll find out. Okay, we'll find out. So let's actually prove those two equations. So, and those two graphs. Before we do this, I'm going to actually look at the physics first, before we go into math and equations. What happens? What happens if you switch that switch from here to A, suddenly throw it to A? That means that you're including the battery. You're including the battery. So at time zero, once you throw the switch to A, what will be the charge on the capacitor? Zero. Yeah. At time zero, just right after you throw it to A. There is no current flowed, so this is still empty. So the The charge here is 0. The potential difference across it is 0. Because if you remember, guys, the relation between C, Q, and E. This is very important. C equal to Q charge divided by the potential difference. Okay? So Q equal to CV. If Q is 0, that means that the potential difference across the capacitor is 0, because the capacitance is only function of the geometry. So the charge is 0. If the charge is 0, we call those two plates an equipotential surface, because the potential difference across them is 0. So we call them an equipotential surface. So those will act like just a wire to us. So after time 0, after you throw that switch to A, this will act like just a wire. And the circuit is E, the battery, and only the resistor. After a very long time, if you wait a very long time after you connect the battery, so what happens? What will be the potential difference across those 2 points? It's not a battery, no. So what will be, what happens? Here, I'm here actually. What happens? So now the capacitor is fully charged in such a way that the potential difference across the capacitor will equal to the potential difference across the battery. It's full charged, and the charge in and in that case there will be no current flowing in the circuit. There will be no current, and if there is no current, that means that this will act like an open switch. Okay, that's when we are charging the capacitor. Now let's look at the physics again when we are discharging it. So I'm going to assume that after a long time of putting the switch to A, after a very long time of putting the switch to A, which means that now the capacitor is fully charged, Sharif, the capacitor is fully charged, then I would suddenly throw the switch from A to B. Okay? Now this, at time 0, once you throw it to B, at time 0, this will act like a battery. The capacitor will act like a battery. And after a very long time, the current is going to flow back in the resistor, and actually it's going to dissipate in the resistor. And after a very long time, there is no current in the circuit. This will act like, again, an open switch. So this is the physics. This is what happens at the two extremes. At time equal to 0 when you throw it to A, and after a very long time, and at time equal to 0 when you throw it to B, and after a very long time. This is the two extremes when we are charging and discharging the capacitor. And before we go on and take your questions, guys, so this is the charge on the capacitor as a function of time. At time Q, at time equal to 0, when we are charging it, the charge on the capacitor is 0, and the charge builds up, then it goes to maximum value after a very long time, after infinite time. And when we are discharging the capacitor, when I say discharging the capacitor, that means that we are starting with fully charged capacitor. At time equal to 0, the charge on the capacitor is maximum. After a very long time, it decays and goes to 0.
C is the maximum.
CE. C times E. Yeah. And if you, yes, to answer you, here, what will be the potential across the capacitor after a very long time? E. What will be the charge in the capacitor? C times E. That's why you have CE in here. Okay, Hussein first.
معلش ممكن تقول لي اول لما واحنا بنعمل تشارجنج اول لما هنفتح هنقفل السويتش الكاباسيتور هيبقى اكتنج like ايه؟
Oh, just a straight wire, simple wire, because there is at time equal to 0, there is no charge on it, and if there is no charge on it, the potential across it will be 0, and anything that has potential difference equal to 0, we call it an equipotential surface. That's a piece of metal. Is an equipotential surface. You had a question first.
I was asking if there's no resistance,
Oh.
and current have
Can I answer that in a minute? After we prove you the equation, it will be much simpler if we get the equation and look at it and examine it. Yes. Kareem first.
In case 1, after a very long time, the capacitor will act like open switch.
Yes. After a very long time, this has the same potential as E. So now the two levels of the circuit is the same. Which direction will the current flow?
Yeah, there will not be any flow in
No,
any
and if there is no flow of the current, this will act like if it is an open switch. Okay? Because we're studying the RC circuit. We have studied how to connect resistors together. We studied how to connect capacitors together. Now this is the time to start how to connect a resistor to a capacitor together. Okay? And RC circuit is part of many circuits that you're going to study in the future. When you go to electronics, computer science, if you get especially into computer science, not computer programming, then the RC circuit is everywhere. Okay? So that's what we're going to study today. This is the behavior of the capacitor when we are charging and discharging the capacitor at the two limits, at time equal to 0 and at time equal to infinity. I'm not going to go over them, but since we know what's going to happen if we connect the capacitor to a resistor at the two extreme, when we talk about time, at time equal to 0 and time equal to infinity, guys, I want you to answer this. Now we have a battery, E, connected to a resistor that has a resistance of 2R, then to a capacitor C, and another resistor parallel to the capacitor C here, and two switches. Rami, I'm sorry, S1 and S2. Now, I'm gonna throw S1 to here. So what happens? What is the circuit that do we have? The circuit now is only E, 2R and C. This is the circuit. And this is a simple RC circuit. A resistor connected to a capacitor. This is a simple RC circuit. Now my question is, what is the voltage across the capacitor immediately after the switch is closed? 0. There's no charge on it, and if there is no charge on it, and we know C does not depend on the Q or V, it depends on the geometry, then that means that the potential difference across the place of the capacitor is 0. And that's the answer. Part 2, find the voltage across the capacitor after the switch has been closed for a very long time. E. Well, the charge will start to build up on the capacitor in such a way that after a very long time, the potential across the capacitor will equal to the potential across the battery, and this is the reason that will not have any current flowing in that circuit, and the capacitor will act like an open switch. Yes. Yeah. Wait. This is closed. When it touches that circle here, that's closed. Open, that it's not touching the circle. Okay. Oh, this is closed circuit. That's why you have C lights in the room. Now, this is an open circuit. I open the switch. There is no current flows. Okay. Okay. Now, same circuit again. After being closed for a long time, the switch 1 is open. So I'm going to open 1 and close 2. And S2 is closed. So I will open this one. Then I will close S2. Now, what is the current through the right resistor immediately after the switch 2 is closed? After we switch after we switch S2 on, after we put it on, after we close it, the capacitor will act like what? A battery. What is the voltage across that battery? E. So now we have a battery connected to a resistor, and the voltage across that battery is E. If we know the potential across the battery, and we know the resistance in the circuit, can you calculate the current?
Yes.
Yeah, what will be the current?
You
E
will.
over R. It's a simple application of Kirchhoff's law or Ohm's law. That's E over R. Rami, yes.
When we close the switch to, is 2R included in the circuit or not?
No, it's not.
It's not. The only included is the E, G, and the R.
Yes. No. It's the only thing in the circuit is C and R. Is C is not there. Yeah, it's not there. Ala. Rami. Ala. Yes.
الكاباسيتنس ادز باتري بس لازم سويتش 1 يكون حصل
Yes, of course. In order for the capacitor to act like a battery, we have to charge it first. If we don't charge it, then it has...
لو اتقفل على طول هو
No, nothing is going to happen. Yes, of course. If there is no, that's what you're asking me. If there is no charge on the capacitor, then it doesn't matter what do you do with S2, nothing is going to happen. That's why I said after being closed for a long time, switch 1 is open. After you close switch 1 for a long time, then you make sure that you have charged the capacitor already. Now you open it and switch 2 goes
The two
on.
switches are closed.
Oh, that's, yeah. Now we're complicating the circuit, and yes, we can answer that. Now we have to find, to answer you, this is not the time to answer it, but I will give you a hint. What is the R equivalent between R and 2R? What is the equivalent resistance in that case? Are they connected in parallel or are they connected in series? Actually, I would say they are connected in parallel. Thank you so much. And now you have to simplify the circuit, draw a new circuit, and now you have one resistor connected to the battery. And yes, they are connected in parallel because simply that point here. So one end of them is connected together, and the other end here. Yeah. Well, can we do this in a minute? But they are connected in parallel. I will prove to you how can we find that they are connected in parallel. The two resistors. Okay, guys. Now let's find. Now we have talked about the physics on what happens at time equal to 0 and time equal to infinity when we are charging or discharging the capacitor. But between those two times, we don't know what happens. We do not have an accurate description of what happened to the charge on the capacitor. And we need an accurate description of what happens to the charge in the capacitor. And that's what I'm going to do. So what I'm going to do is I will assume, for simplicity, I'll do a little bit different than the book. For simplicity, I will start assuming that I have a fully charged capacitor. A fully charged capacitor. And I'm going to study discharging first. This is much easy. Then studying charging first. The book starts discussing that we're charging the capacitor and give you all the equation. Then the second part is discharging the capacitor. I will reverse that. Same thing. But this is much easier in mathematics. So in here, I'm going to assume that I have a fully charged capacitor, which means that the potential difference across the capacitor is E. Okay? And the maximum charge, so the potential difference across the capacitor is E in that case. And the maximum charge available on the capacitor, that's CE. Keep that in mind. That's from that equation. Now, we're going to apply Kirchhoff's voltage law on that circuit, on that loop. Sharif? Let's apply Kirchhoff's voltage law on that loop. What does Kirchhoff's voltage law says? Omar? What does it say? The law. Mahmoud?
في حاجة يكون equal zero بس مش عارف اسمها ايه.
Lina? That's the Kirchhoff's current law. Why are we doing this? Why are we saying this? Yeah. Then we add what?
Potential across
Yes, Amr?
sum of one potential across a closed loop becomes zero.
Yeah, sum of the potential equal to zero. Sum of the potential across any closed loop equal to zero, and this is the conservation of energy law, by the way. This is the conservation of energy law. So sum of the potential across the loop is equal to zero, so the potential drop across the resistor drop, that's why I put a negative sign here, minus the potential drop across the capacitor equal to zero. This is Kirchhoff's voltage law for that loop. So I will rewrite that again, minus IR minus what is the potential drop across any capacitor? It's Q over C. It's the charge on the capacitor at any time. It's the charge on the capacitor at any time over C. This is V, the potential at across the capacitor equal to zero. Right? Good. Does anyone remember? Yes. At any time. No, at any time. At any time. This is the potential. So at time equal to zero, at time equal to infinity, what is the charge on the capacitor? Zero. This is charging. Yeah. What? Zero. And the potential will be zero. At time equal to zero, when we are discharging, what is the charge on the capacitor? CE. So what will be the potential on the capacitor? E. So this is the definition of the potential on any capacitor at any time t. This equation is valid at any time t. Okay? It's valid at the beginning or after a very long time or any time between them. Okay? Can anyone tell me what is the definition of a current? Charge per unit time. So the current is nothing but the flow of the charge with respect to time. It's dq by dt times R minus Q over C equal to 0. So look at that equation again. Now I have a differential equation. If I can solve that differential equation, I will find the charge at any time t. So our goal now, it's gone beyond physics into mathematics, which is how to solve that differential equation. Hussein. The charge on the capacitor at any time t. Q is the charge on the capacitor at any time. At time equal to 0 or at time equal to 1 second. Oh. If I tell you the time, you can calculate Q. Let's just finish this first. Does anyone know how to solve that equation? Oh, come on, guys. You studied that. Ala, you know how to do it. So guide me through. Guide me. Just guide me. Tell me what to do and I will do the writing. So Ala said it's dq by dt equals Q over RC. What did Ala do is he divided that whole equation by R. Nothing more than that. And he rearranged the equation. He moved that part to the other side. Ala is doing what we call it in mathematics variable separation. We're going to separate the variables. We have two variables in that equation. Hisham. What's your name? I forgot your name. Tariq. It's Ahmed Hisham, yeah. dq over dt. Those are the Q and T. Those are the two variables. And I'm going to separate them. So Ala is saying, Ahmed is saying dq over Q equal to dt over RC. Ahmed, can you do this? Yeah, good. dq over Q equal to minus dt over RC. Then, what didn't you understand?
The last part, how did you, first step, second step?
What do you think? Omar? Yeah. Just separated the variables. We got all the Q's in one side, all the T in the other side, and that's it. Okay? Tariq. Then, we need to find Q. So all what we do is to do an integration here and there. That integration, we start with a charge equal to Q maximum, and we end up by a charge equal to Q at any time T. Small q is the charge at any time T. And we start by time equal to 0, that's the beginning, and till time T. So if we do that integration, we should be able to find what will be the charge at any time T. What is the integration of dq over Q, guys? Wait. Yeah. Wait. Just wait. Minus 1 over RC is constant, goes out of the integration. What is the integration of dt? Just d. Okay, guys? Then, what to do? Tariq? Right? So it's len Q over Q max equal to minus T over RC. In order to get rid of that len, everything to the power E, so this is going to be Q over Q max equal to E to the power minus T over RC, or Q equal to Q max times E to the power minus T over RC. Yeah. This is the equation that describes us Q, the charge on a capacitor, at any time T. Just tell me the T. What is the time T that we're talking about? Tell me what is the value of R and C. I will be able to find to you what will be the charge on a capacitor at any time. Okay, guys? Okay? Yes. No, it's in the book. It's in the book. You don't have to write it. It's simple. All what we did is, this is the most important part. Where to start? What to do? Kirchhoff's law. Then the rest, you can do it. You don't even have to write it. Sure. Charging, you mean? What other side? What other side? Oh, okay. Positive. No. There is a potential drop across the resistor. There is a potential drop across the capacitor. That's why both of them have negative signs. So now we have the equation. Look at that equation. I want to examine that equation, then go to what Omar said about half time, which is time that to reach the max, half of the maximum charge on the capacitor. But that's not important now. Look at that equation. At time equal to 0, this term is 1. And the charge on the capacitor is Q maximum. At time equal to infinity, that term is 0. 0 times Q maximum, you get charge 0 equal to this is the charge on the capacitor. So actually what we have talked about the physics at the two extreme time, at the beginning and at the end, is valid by that equation. This equation described to us, let me finish. This equation described to us the charge on the capacitor at any time t when we are discharging it. So we charge it for a long time, then we disconnect the battery, and we observe what happens. It has to follow that equation. It decays after time. Guys, before we move on, can you guys tell me what will be the current in the circuit? We need to describe the not only the charge on the capacitor, but I need to describe the current in that circuit as a function of time. Yeah. So Hussein is saying, well, since the charge is a function of time, then the current in that case will equal to dq over dt. So it's d by dt for the charge, which is q maximum e to the power minus t over RC. How many of you guys can do that derivative? Just raise your hand. Kareem, Omar, can you do that derivative? Oh, okay. Simply, it's two functions multiplied by each other. One of them is constant. Q maximum is constant. So it stays as is. Q maximum. The derivative of any e d by dx for e to the power minus, so e to the power x, it's e to the power x times d by dx for whatever in here. Yeah, in that case it's 1. So if it was x over 2, this is going to be 1 over 2 e to the power x over 2. So the derivative of that e to the power minus t over RC, that's RC negative. Remind me again, what's Q maximum over C? What V? Which V? E. So this is going to be minus E over R times E to the power minus T over RC. This is the current as a function of time t. Yeah. dq by dt, that's the current. This is the definition of the current. Any current is the difference in the charge divided by the difference of time over. Yeah. I started by doing that same thing. I replaced I by dq by dt. Yes, the derivative of that equation, and that's what we got. So this is the current. Let's look at the current again. Potential across the battery. Yeah. Oh yeah. Yes. You have to understand what happened. There's no proof. It's only a simple integration. Yeah. There's no proof. Again, let's examine the current. Look at the current. At time equal to 0, this term is 1, and the current is minus E over R. At time equal to infinity, that term is 0, and the current is 0. Okay. Good. That's a very good question in here. Can you answer it to me after I get the other part of the circuit? When we are charging the capacitor? That's a very good question here. Why we get negative current? What does the negative current mean, guys? Yeah. It means that I have assumed that the current is flowing in that direction, but from my solution, the current actually is flowing in the other direction, and it makes sense. If this is the battery now, the current is should flow in the other direction. Yeah, yeah. But we got that already from the equation. So if you assume that the current is flowing in that direction or the other direction, you will get that from the equation. So no worries about it. Yeah. No, you will get the answer. If you assume that the current is flowing in the other direction, then I is going to be E over R, not negative. You will not get the negative sign. Anything Both of them are correct.
when I'm solving any
Problem in the exam.
problem, I don't put the negative sign.
No, I didn't say that. I said that if you assume the direction of the current either clockwise or counterclockwise, and you follow the same methodology, you will get the right answer. You will get the right answer, whatever the answer is. This is the right answer. And the negative sign tells me that the direction of the current is in the opposite direction to my assumption.
القارن بقى لما عليها
You will not get the negative sign.
الفاينانس ما فيش منك
You will, no.
Derivation مش هيجيب لك
Yeah, when you drive it again, the derivation will not give you the negative sign.
ده امسح بقى واقعد
No, no. Did I erase it and start it over again because I?
سيبه زي ما هو بس تقول له القارن عكس
Yeah, yes, yeah. When I did that, I got a negative sign, and the negative sign told us that the current flowing in the circuit is in the opposite direction to my assumption. That's all. Then I know now what is the direction of the current. Okay? You don't have to repeat the whole thing again. You just got it.
دكتور انا عندي سؤال.
Okay.
ودلوقتي لو انا مفيش سويتش و اي ام اف عادي والاي والار والسي كونكتد بالسيريز.
So if you are charging the capacitor,
لا مش تشارجنج مفيش سويتش.
yeah,
ده اجيب الفولتج عادي.
yeah. If the switch is at A, right? If the switch is at A, that means that you are charging the capacitor, and we're going to do that in a minute.
زي ما ينفعش اقول ان الار والسي كونكتد بالسيريز او بارلل عشان اجيب الفولتج اقول مثلا ان الار والسي كونكتد بارلل او سيريز.
Those are connected in the two cases, either charging or discharging. They are connected in series.
ممكن بقى اعملهم اللي هو بالرول بتاع السيريز ده عشان
No. You cannot. You can do the. So you want to say that the resistance here and the resistance here are. This does not have a resistance actually. It has something else that we're going to talk about it later on when we study magnetism. Capacitor has something else. We do not call it resistance. Impedance. We'll talk about impedance later on, not now. But I cannot assume that capacitor is a resistor. I cannot assume that because it's not a resistor.
هو لازم اعمل حاجه.
Yes. So guys, I have applied Kirchhoff's voltage law, Tariq, and actually I did not. This is Kirchhoff voltage law. Then I said that the current is dq by dt. I replaced I in that equation by dq by dt. I got that equation, and if we solve that equation as we did on the board, you get that equation. That is the solution. This is the charge as a function of time t. The charge equal Q maximum, that's CE or Q0, whatever you call it, times e to the power minus t over RC. And we have and we have examined that equation at the two extremes, at time equal to 0 and time equal to infinity. And we were able also to get the current afterwards. So, this is the current. This is the charge as a function of time, and I'm going to draw them. The charge, you start with the maximum charge, that's CE, and it decays with the time till it goes to 0 at a very long time at infinity. And this is the current. You start with the current, E over R, and the current decays till it goes to 0 after a very long time t. And remember that current is in the opposite direction to the original current, because if you are charging the capacitor, let's get the circuit back. If you are charging the capacitor, the current is going to flow in that direction. It's going to flow clockwise. When you discharge the capacitor, the current is going to flow counterclockwise. That's why you get that negative sign here. Omar said something about the time. Time at half constant. Time at half of the maximum charge. I'm not really interested in this. And what we are interested more is what's going to happen if the time Look at that equation again. Look at that equation again. Look at that equation again, guys. What is the units of RC? And what ohm farad? No, Henry is something for a coil later on. Seconds. Actually, the units for RC has to have the units of T. This whole thing here, has to be unitless. It's just a ratio. Otherwise, the equation will not be correct from the point of dimension. This has to be unitless. So this RC has the unit of time. So if the time equal, at time, if you leave that circuit on, for time equal to RC, what will be the charge on the capacitor? So if you leave that circuit working for time equal to RC, what will be the charge on the capacitor? Well, that's very easy. That's not difficult. So what I'm going to do is, I know that the equation that gives me the charge at any time t given by Q equal to Q maximum times E to the power minus T over RC. And if you're asking me at time equal to RC, what will be the charge? Then it's going to be Q maximum times E to the power minus RC. I replace the time by RC divided by RC. So it's going to be Q maximum times E to the power minus 1. It's Q maximum times, as Hussein said, 1 over E. What's E? 2.7 blah 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 blah. So if you put the value for E, you get what will be the charge on the capacitor after time equal to RC. And the charge on the capacitor will equal to 37% of its maximum value. It's 37% of the maximum value. So after time equal to RC, the charge on the capacitor will equal to 37% of its maximum value. It's 1 over E. And we get that from here. Let's assume that R is equal to 100 ohm, C is equal to, yes.
So it's like one, RC has a specific value here.
Yeah.
Compared to RC, but it's constant in any graph, RC.
Yeah, of course. For any circuit, you have to choose a resistor and a capacitor. And if you choose a resistor and a capacitor, they have to have values. So if I know those values, so after time equal to R multiplied by C, you can simply find what will be the charge after that time. That time can be milliseconds. That depends on the values of R and C. Okay? Yeah. Yes. Just calculate R and C, and whatever the R and C is, the Q, yes, is always 1 over E of the maximum value after time equal to RC. Amr, okay? Okay. And same thing goes for the current. Guys, that time, Amr, that time, when T equal to RC, this is one of the characteristics of any circuit. So we call it tau. It's time constant. The time constant, tau, which is equal to RC. So just give me the value of RC for any circuit, I will be able to calculate for you the time constant. Again, the definition of the time constant in that case, it's the time needed for the charge to fall down to 37% of its maximum value. 37% of its maximum value. This is the definition of a time constant. So after one time constant, in here, when we are discharging the capacitor, the charge will be 37% of its maximum value. Now, look at this. Two resistors, R and 2R, connected to this to an identical capacitor, C and C. Now we have two circuits and we need to compare the charge on the two capacitors after a short time, 0. So the two capacitors of course are charged. We charge them, they are fully charged. Then we insert them in that circuit. One is connected to R and the other one is connected to 2R. And I need to know which one will have a charge more than the other one after time equal to 0. Who said that? Sharif. Sharif said QA is the answer. Then Amr is saying no. It's Q2 will have more. I'm not discussing the reason now. I'm just getting which one is the right answer. Then we'll go back and find out the reasons. So Sharif is saying A is the answer. Amr is saying C is the answer. C. Sharif. Sharif changed his mind and he's saying that actually B is the answer. The two charges will be the same. So now we have three answers. That's even better. How about none of the above? How about none of the above? Okay, guys. So let's start. Who wants to start to explain his answer? Sharif? You said? So at time equal to 0, it's e to the power 0. Q is equal to Q max. Q is equal to Q max. Yeah, that's true. At time equal to 0, the charge in the capacitor, it's the maximum charge. And if they have the same capacitance and they have the same capacitance, same everything, then they should have the same maximum charge. Oh. Wait. Oh, I'm sorry. Yes, at time equal to 0. After a short time after t, so after a very small short time after t, Sharif, you're right. At time equal to 0, you get the two charges are the same. But after a very short time, so not at 0, after spending a little bit of time, what will be the charge? Why? So? Can I ask you something else, guys?
What's the physical behind that?
No. If we have two circuits, Ala, if we have two circuits, one of them has a time constant than the other one. One of them has a time constant more than the other one. RC. One of them has a time constant more than the other one. What does that mean? True. What else?
Means in the charge has decreased to a certain point and time more in one time more than the other.
Yeah. Kareem is saying that means that one of them, the charge will take longer time to decay than the other one. That's what you're saying. Which one will take longer time to decay?
Has greater time constant.
The one will have greater time constant. The one with more time constant, the one with more, it will take more time to decay. So if we draw, I know Henny hates the red when he, this is the time, this is the charge on the capacitor. If we have two circuits, one of them decays like this and the other one decays like that. Which one of those has more time constant? Yes, that one. This one have an RC more than RC. This is 2 and this is 1 more than RC1. It takes longer time to decay.
Doctor, if we did it with this,
Mm-hmm.
we put 2RC with E over RC.
Uh-huh. And assume any current. So you're saying If I put here R or 2R and assume any current, 1 second, in the two cases, then which one will have more Q? The one with more resistance. So you have to actually look at it from the point of time constant. The one that has more time constant, it decays in a longer time. It takes time to decay. The one that has a very short time constant, it takes fast time to decay. It decays faster. Short time constant, the charge decays fast. Long time constant, the charge decays very slow. That's it.
انا دكتور لو حطينا في السيركت دي قعدنا نحط الريزستنس دي اللمبه هتفيد
Yes. Yes. So if we change the resistance and put a smaller resistance, then it would decay. It would decay faster.
faster.
Yes. If listen again what I'm saying, because you're listening only half what I'm saying. If you change that resistor to another one with a smaller value, then yes, the current will the current and the charge will decay faster. Lena. Lena.
ممكن أفهم ohms law.
No.
D equals RR to the RA equals the
No. It's not a simple Ohm's law in here. It's not a simple Ohm's law here. Both of them have the same potential. This and this, they have the same potential. Same charge to start up with, same charge to start up with, same capacitance, then the same potential at them at time equal to 0. So it's not that easy by Ohm's law. Yeah. Yes, that's right. Now at time equal to very short time here. You can compare now between the times. This has a Q and this has a Q. Which one has more Q? Yeah. Yeah. The one that has longer time constant. Yes. In that case, the one that has more resistance, because we fixed the capacitance in that case. علاء.
لو واحدة 2R وسي واحدة سي واحدة R وسي
What did he say? Say it again, please.
لو واحدة سي 2R
C and 2R?
واحدة R وسي ولا سي.
Yeah, of course, the same. And that was one of my problem of one of my older exams. Okay? Since you got the solution for the exam, can you solve that one? علاء. A capacitor in the circuit shown is initially charged at Q equal to Q0. So the capacitor has a charge initially equal to Q0. At time equal to 0, the switch is connected to A. So we throw the switch to A. Then after waiting for a time equal to T0, after waiting for a time equal to some time T, I will call it T0, we switch the switch from A to B. So first we throw it to A, we wait for some time, then we throw it to B. And Hani has connected that to some fancy software so we can draw that curve, Q as a function of time. One of those three curves is correct. Q as a function of time. Q does depend on the time. Q0, of course, Q0. Start from maximum charge, Q0. Q0, Q0. Wait. Just give them a minute to think about it. Wait. Wait. Guys, do you understand the problem? Omar, do you understand the problem? We first throw to A, then the charge will decay, then suddenly we throw it back to B, then the charge will decay, but the decay time in both of them, the time constant is going to be different. The rate of decay is different in both of them. And since I said that the rate of decay is different in both of them, this is wrong. Because this assumes that they, two of them will have the same decay rate, which is not the case. Which one will take longer time to decay? Which case? That one, when we throw it to B. So that curve will have to move to be more flat. So it has to go fast first, then slower. Now you know the solution. Now you know the solution. And that was also one of the exams. So you have to think about the physics. It's not math. Of course, you can prove it by mathematics all the time. And you can get the same thing again. But if you use the physics first, it will save you a lot of time. Okay, guys? Yeah, but it will save you a lot of time. If you do try it, it will save you a lot of time. If you understand what's the problem, what is the problem, and how can you approach it, then it will save you a lot of time. Okay, which of the following correctly relates the value of 2, 0 to the constant time t? Part B, guys. Which of the following correctly relates the t0 to the constant time t while the switch is at A? So tau is the time constant when it's at A. So which one relate t0 to tau? Again, remind me, what's tau? Yeah, what does it RC mean? What does tau mean? Physical meaning. Time to decay to what? 37% of the maximum value. So at 1 tau, the charge will be here. This is 1 tau. This is 1 tau. We said A, right? So if the curve like this is 1 tau. Tau is somewhere in here. Now can you relate T0 to tau? Tau is more than T0. So yeah. The definition of tau, time constant, is the time needed for the charge to decay to 37% of the maximum value. So this is 50%. This is 37%, somewhere in here. So if the curve continues like that, if the curve continue like this, then tau will meet the curve at that point. Now this is tau. Now can you compare T0 to tau?
Then I compare time time, tau is greater than T0. Not time.
What? Okay.
We compare that.
Okay. T0 is the time, is the time that we switch from A to B. That's T0. Tau is the time constant. Time constant, yes. And definition of time constant for the circuit 1, it's the time needed for the charge in the capacitor to decay to 37% of its maximum value. So after waiting for time tau, the charge on the capacitor will be 37% of the maximum value. So this is 100%. This is 50%. 37% is somewhere in here. So if that curve if it continues like this, then tau is that point.
Tau is greater than
Yes, and that's the answer. This is A, as you said, guys, and that's no. Okay, guys, the second part of this is what Ala was asking a minute ago. What if we are charging this? If we connect it to A, what happens? if you connect the switch to A in the circuit, remember we connected it to B and we calculated the charge and the current in the circuit and the charge on the capacitor. Now we're going to actually start the other part when we are charging the capacitor.
دكتور هو ايه الاصفر ده؟ يعني المفروض ان يتنور
Here. So now we connected it to the battery. When we connect it to a battery, it takes time for the charge to build up on the capacitor as well. Now we need to calculate the charge as a function of time as well in that case. So what to do? We'll see. We'll see. So I'm going to start again by the same way. We'll write down Kirchhoff's voltage law and Sharif. E minus the drop in the potential across the resistor minus the drop in the potential across the capacitor will equal to 0. This is Kirchhoff's voltage law. Then what? Replace I by dq by dt, you get this. Replace I by dq by dt, you get that equation. Then what? Separate the variables. Separate the variables. And if we separate the variables, solve the equation again using some integrations. This is you can find that in the book, or you can just repeat the same thing again. I'm not going to do it again. Either you do it again, guys, as we did on the board, or just read it from the book. It's not a big deal. Sorry? Are you okay with it? Or should I do it? Yes. Yes. The only thing is you have an E in here, and if you solve that equation, you get this solution. Q equal to Q maximum again, C times E, that's Q maximum again, times 1 minus E to the power minus T over RC. Now let's examine that equation. At time equal to 0, this value is 1. 1 minus 1 is 0 times anything, the charge on the capacitor is 0. So as we said at the beginning, guys, when we started that lecture, we said at the beginning, there will be no charge on the capacitor, and this will act like just a wire. Just a wire. So actually, the charge on the capacitor at time equal to 0 is 0. After a very long time, what will be the charge in the capacitor? This quantity is, at time equal to infinity, 0. 1 minus 0 is, so 1 times maximum charge, you get maximum charge on the capacitor. Now, can we find the current? The current, yes. Just the derivative of that equation will give us the current. So dq by dt equal to CE times, the derivative of that is 0. The derivative of this term is minus 1 over RC times e to the power minus t over RC. Again, this is the equation that will give us the current. I will draw them. Q equal to Q maximum times 1 minus e to the power minus t over RC, and I equal to E over R times e to the power minus t over RC. Now let's draw those two equations. At time equal to 0, this quantity is 1. 1 minus 1 is 0. The charge on the capacitor is 0. After time equal to infinity, after a very long time, this quantity is 0, and the charge on the capacitor is Q max. In that equation, at time equal to 0, this quantity is 0, e to the power 0, sorry, is 1, e to the power 0 is 1, this quantity is equal to 1, 1 times E over R, then the current is maximum actually. The current is E over R. And it makes sense. If you include another device in the circuit, you slow the current. So at time equal to 0, the current is maximum. After a very long time, at time equal to infinity, e to the power minus infinity, it's 0. 0 times E over R, you get 0 current. And this is the curve. Again, Omar, we're very interested in finding how much charge will be on the capacitor when we are charging it, not discharging it. So I'm going to assume that the time again at time equal to RC, at time equal to tau. Well, how much charge will be on the capacitor when we are charging it? We know that when we were discharging it, we got 37%. Now let's charge it and find out how much charge will be in there. Yes, you're right. Let's do it. So, Sharif ask.
63 years separated 100%?
63 is? No, but we did not get it that way. That's how we got the 63%. We said at time equal to RC, e to the power minus RC divided by RC, that's e to the power minus 1, which is 1 minus 1 over E. 1 over E is 0.37. 1 minus 0.37, that's 63% times the Q maximum. You get 63% of the maximum value. So at time equal to one time constant, when we are charging the capacitor, you will have 63% of the maximum value. That's why, guys, if you noticed, when we charge it, it reached the maximum 63% in only one after only one RC. When we decay it, almost you know, it's high value. High value. After we connect it, هنا في حاجة. Yeah, here you go. Okay. Sharif, when you connect text to reach the maximum, it goes very fast. When you decay it, بس مش شايفينها.
جنبها ايوه. لا في حاجه جنب دي مش توصلها او مش توصلها احسن.
طول لفها بقى.
دي كده كده ممكن. صح. كده
Okay. So after one time constant, the charge go really fast, go to maximum really fast after only one time constant. But now you get only 37% on there after one time constant.
It means in the power, it's working يعني like 60% of its power.
When you mean that you have stored on the capacitor 63% of its maximum value. You can store in the capacitor a specific amount of charges. Okay? So after one time constant, you get only 63% of the maximum there. And when you decay it, you decay only 37% after one time constant. Okay, guys, before we leave, one more problem, then we will leave. At time equal to 0, the switch is thrown from B to A. At time equal to 0, the switch is thrown from B to A. The capacitor is initially uncharged. At time equal to T1 equal to tau in that case. The charge Q1 on the capacitor is 1 minus 1 over E of its maximum value. Okay. At time equal to tau, the charge on the capacitor will equal to 1 minus 1 over E of its maximum value. Because the equation says this is charging. This is charging. For charging, Q will equal to Q maximum times 1 minus E to the power minus T over RC. This is charging, this is charging. Okay? I'm saying that at time equal to tau, which is RC, this quantity is going to be 1 over E. So the Q will equal to Q maximum times 1 minus 1 over E. That's what I'm saying.
The quantity
This is going to be 1 over E. Yes.
T equal RC.
Yeah, that's what I'm saying. At time t equal to RC, this whole quantity will be 1 over E. So if you plug it in here, you get that equation in here. What is the relation between Q1 and Q2? And where Q2 is the charge on the capacitor at time equal to 2 tau. So in that circuit there, we have R connected to C, connected to another R, back to the battery. And I need to compare the charge on the capacitor at time equal to tau and the charge on the capacitor at time equal to 2 tau. Graphs are very useful in that case. Graphs are very useful in that case. So I'm going to assume this is charge as a function of time. Now, we're building the charges on the capacitor. So that's what happens. That's tau, 63%, and that's 2 tau. Which one will have more charge, tau or 2 tau? And will that charge equal to twice the charge at 1 tau? Never. Never. Yeah, twice the charge will equal to 1.2 of the maximum charge. Can that happen?
So at 2 tau, charge in the capacitor.
Oh.
Is it over 100%? It reaches the maximum? No.
2RC, Omar, 2RC. So this is Q equal to Q maximum times 1 minus e to the power minus 2. Can you do it? Can you calculate it? That's a very simple calculation. But it's going to never be 100%. It has to be less than 100% anyway. So the answer is not going to be that or that. And you have the solution here, you can look at it later on.
2Q1 ده يعني معناها انها كانها restricted 3% multiplied by 2.
Yeah. And that slide, guys, summarize all what we have studied before. Charge when we are charging, current when we are charging, charge when we are discharging, current when we are discharging. Guys, in the exam you get those 4 equations written. But I don't tell you which is which. And it's easy for you to figure out. Yeah, I give it to you in the, no, equations. I don't give graphs unless it's really needed in the problem. But let me tell you before you leave, let me tell you before you leave how can we differentiate between those 4 equations. If you understand what happens when we are charging and discharging, you can examine the extreme cases in any equation. So if I don't know if this is charging or discharging equation, I put time equal to 0. So at time equal to 0, what is the charge on the capacitor? Is it? And time equal to infinity, what is the charge on the capacitor? So obviously this is the equation that describes the charge on the capacitor when we are discharging. So even though I give it to you in the exam, but it's very easy to differentiate between them, which is which in the exam. E to the power minus infinity, 1 over infinity, which is almost infinity, which is infinity actually, e of the power infinity is infinity, so 1 over infinity is 0. Okay guys, thank you so much for coming.